So earlier, we had said that water was amphoteric. And that means that water can behave as both an acid or a base. So believe it or not, water can actually react with itself. And it doesn't happen a lot, okay? At 25 degrees Celsius, at 1 atm. So what I'm really writing out are basically standard conditions, just like standard temperature and pressure, okay? These are standard conditions. At 25 degrees Celsius and 1 atmosphere, about 2 out of 10 million water molecules react. And what does this double arrow mean? It's only what? Partial dissociation, right? This doesn't happen a lot. How often? Only 2 out of 10 million. But it does happen, end up producing, right? So one water accepts the proton and one donates it, right? The way they wrote it, they kind of switched it. It would make more sense had they made this one the donator, because the H3O hydronium's here, but whatever. One of them accepts it, one of it donates, and what do I get? The hydronium ion and the hydroxide. Well, how much do I get? 1 out of, well, this is a 1-to-1 mole ratio. Hydronium to hydroxide in the balanced equation. What is that? Is that a 1-to-1 mole ratio?
Yes.
Okay. And I said, so 2 water molecules do this out of 10 million. So I get 1 hydronium out of how many? 10 million, right? So at 25 degrees Celsius, 1 atmosphere, from 10 million water molecules, right? And I'm going to make this easy. I'm going to use scientific notation. Didn't we learn that? So I didn't have to write so many zeros. Right? So 10, isn't that 10 to the 7? If I use scientific notation? It doesn't happen a lot, but 1 out of 10 to the 7. I get 1 hydronium ion out of 10 million water molecules, and I get 1 hydroxide ion out of 10 million. But typically in exponents, we don't want exponents in the denominator. So how would I make 1 out of 10 million, but put it in the numerator? What's the rule for exponents? How do I do that again? What do I change the value to? Instead of positive, it becomes, the chat is
positive becomes negative?
Yes. So a way to say 1 out of 10 million is me saying 1 times 10 to the negative 7. So at 25 degrees Celsius and 1 atmosphere, right, only 2 water molecules out of 10 million will react to give me 1 hydronium ion out of 10 million, which is 1 times 10 to the minus 7. And same for hydroxide. You guys see that?
Yeah.
So why is that interesting? Well, in pure water, right, we're going to produce a very small amount of hydronium and hydroxide. What was that amount? Wasn't it just 1 times 10 to the negative 7? And we're producing them in equal amounts because their mole ratio was 1-to-1. So we could write 1 times 10 to the minus 7, big M. What does big M mean again?
Molarity.
Molarity, moles per liter. So I could say I have 1 times 10 to the minus 7 moles per liter of hydronium concentration, which is also equal to my hydroxide. Now, we had just talked about how do we measure acidity? We measure it by the presence of hydronium. Well, how do we measure base? The presence of hydroxide. Well, if they're in equal amounts, what does that make them? Neutral, right? If I measure acidity from hydronium ion and its relationship to the hydroxide ion determines whether or not it's an acid or a base. And the two things that I measure are equal. So what I measure acids with and what I measure bases are equal, then it must be a neutral solution, right? So what we find is that neutral solutions have the same concentration of the hydronium ion. Now, where did I get this number? I told you, at 25 degrees Celsius, 1 atm, 1 or 2 out of 10 million water molecules will dissociate, giving me one of these and one of these. So neutral solutions, 10 to the minus 7. You know what's really interesting? What pH is a neutral solution? Does anybody know what the pH for a neutral solution is?
7.
Anybody out there?
7.
Yes, a neutral solution has a pH of 7. Oh, you mean like this exponent right there? That's a trick.
Oh, is that how we calculate it?
It's going to be a negative log, my friend. I'm building up to it. I'm deriving it for you, homie.
Oh.
Yeah. Here we go. Okay. So the molar concentrations are indicated by brackets. I've already talked about that in chapter 8, right? And we know that the molar concentration is 1 times 10 to the minus 7 for both in equal amounts. That's why this is neutral. So we can make what's called a product constant. It's referred to as Kw. So a lot of times you learn about equilibrium constant K prior to acid-base equilibrium, but that's okay. We're going to do it anyways. But Kw measures, right, the amount of hydronium. So specifically, if they're equal, we can make an ion product constant for water. And how do we do that? Well, we say the constant is Kw, and we set it equal to the two hydronium, or to the hydronium concentration in the hydroxide. And didn't I just say that, the hydronium concentration is 10 to the minus 7 molar, right? And the hydroxide's equal, right? And what are the rules of exponents? Like if I had x squared to q. Yes. See, that math is coming back. You add, right? Because 2 plus 3 is 5. Well, what's negative 7 plus negative 7?
Negative 14.
What do you think Kw is, my friend? It's 1 times 10 to the minus 14. So the hydronium concentration and the hydroxide concentration in water, or aqueous solutions for that matter, at 25 degrees Celsius, when we multiply those, we get 1 times 10 to the minus 14. Now, why is that important? We can kind of determine what happens in acidic conditions if I take an acid and I throw it into water. So like if I take HCl and I throw it in water, what is the HCl going to do? How is water going to act? If I have pure water and I throw a bunch of HCl into it.
Disassociate?
The water won't dissociate, the acid will. So how does water behave? This
Like
acid,
base?
like a base. So the water, right? If the HCl donates a proton, right? If the HCl donates a proton, what do I produce? The hydronium ion and the chloride, right? Didn't we just do that? Water is behaving as a Bronsted-Lowry base, and its conjugate acid is hydronium. So when I throw a bunch of hydrochloric acid, what happens to my hydronium concentration in water? It goes up.
Hydronium.
More hydronium, that's right. So what people don't understand is, well, if I add also a bunch of HCl to the small amount of hydroxide, because remember, I had in pure water 10 to the minus 7, right? Times 10 to the minus 7 molarity of hydroxide. But to that small amount of hydroxide, if it actually finds some of the hydroxide, the acid will protonate it because it's a base, and it will produce water and the chloride ion. So what happens to my hydroxide concentration? It goes down. So when I add acid, hydronium goes up, hydroxide goes down. And what does that mean? They are inversely related. Now, I see that I'm getting more than 1 out of 10 million moles per liter. That must mean if I have more hydronium, it's acidic. And at the same time, the hydroxide, because it's acidic, decreases. So what do I notice here? When the hydronium concentration is bigger than hydroxide, it's an acid. Well, how would I get that? Well, I'd have to add acid to it, like hydrochloric. Well, what would happen if I add a base, right? Let's say I added sodium hydroxide, right? If I took this salt, and I throw it in water, what do I end up getting? I get a bunch of hydroxide added. So this goes up, right? Some people are like, well, how does hydronium go down? Well, if there's a bunch of OH minus floating around and it happens to bump into 1 out of the 10 million hydroniums, that will donate a proton and then end up producing 2 water molecules. So it just decreased that. So when hydroxide increases, hydronium's it's gonna be, or the hydroxide will be bigger than 10 to the minus 7. The hydronium will decrease. And what do I see? The hydroxide concentration is greater than hydronium under basic. So what do we know? When these concentrations are equal, I'm neutral, right? If I add a bunch of OH minus, right, because I'm adding a base to water, if I add a base to water, this is going to go up and some of it's going to react with the hydronium, so that will decrease. If I add acid, right, and how do we determine acid? Proton donor. I'm going to donate a bunch of protons to water, so this is going to go up, and I'm going to react with some of the hydroxide to water, that will go down, right? So when they're equal, and what was it equal? 1 times 10 to the minus 7, right? If hydronium is bigger than 1 times 10 to the minus 7, maybe it's like 1 times 10 to the minus 3. Now people get confused because they go 3, that's smaller than 7. Yeah, but it's closer to 1, right? Because 1 times 10 to the 0 is just 1 molar, right? 10 to the negative 2. 2 is bigger than 0, but when it's a negative exponent, it's really saying this. So negative 2 is 0.01 molar, which is less than 1 molar, right? And then if the hydronium concentration is less than hydroxide, so less than this, it might be like 1 times 10 to the minus 10 molar. Does anyone know how the pH scale is kind of measured? Isn't it 0 to 7 is
0 to
acidic?
7. Yeah.
And
then
7 to 14 is
basic.
Yeah. Where do we get the 14? Remember what KW was? KW was 1 times 10 to the minus 7, right? From the hydronium and the hydroxide. So if I square it, 1 times 10 to the minus 14. That's where I get that number from, right? And the 7, do I get these two? Right? So if they're in equal amounts, it's neutral. If there's more hydronium, so like a pH of 3, that means it's acidic. If it's a pH of, wait, what's that number right there? 10. What does that make it? Basic. So we're looking at the exponent to figure out the pH. So in acidic solutions, we have more hydronium. In basic solutions, we have more hydroxide. So even though these go, if this goes up, my hydroxide we saw must go what? Down. If hydroxide goes up, my hydronium goes down. Why? Because both of them have to equal Kw when you multiply them. So they are inversely related. And we're going to use Kw and the hydronium and hydroxide concentrations and that to figure out in different acidic and basic conditions what those concentrations are. So that will be next time. So next time, we'll take advantage of the Kw value and we'll solve specifically for hydronium and hydroxide concentrations. Once we can solve for hydronium and hydroxide concentrations, we will then solve for pH, because pH is the negative log of whatever the hydronium ion is. All right, so today we learned neutral water, right, is 1 times 10 to the minus 7 for this, right? And if I wanted to do pH, if I hit log 1 times 10 to the minus 7, I'm going to get negative 7, because on your calculator, log is base 10. You would just hit that log 1 times 10 to the minus 7 equals, you get a negative 7, because that's what the exponent was. And then the negative in front cancels negatives and gives you a pH of 7. So what we're finding is that pH is the negative log function of the hydronium concentration. And Kw, because it is a constant, allows us to solve for this. And if hydronium goes up, hydroxide goes down.